Around 200,000 tons of aluminum are produced every day. The United States alone consumes more than 4.6 billion kilograms per year. To meet this colossal demand, millions of tons of ore must be processed. But how does a reddish rock transform into one of the most precious metals on the planet? In this video, you will discover where aluminum comes from and how it is made. Without it, civilization could not survive. This marvel of engineering is everywhere. Aluminum is an essential element of airplanes, automobiles, and high-voltage cables that carry electricity to our homes. Unlike iron, which oxidizes and deteriorates over time, aluminum forms a layer of aluminum oxide on its surface that protects it from corrosion. It is 3 times lighter than steel. Thanks to its low density and high strength, it became the main material for aeronautical construction. However, it was only in 1807 that British chemist Humphrey Davy first identified a metal in a salt called alum. Its identification was easy, but isolating it proved a major challenge. It took about 20 years for Danish chemist Hans Christian Ørsted to extract the metal. Yet the process was so complex and costly that at the beginning of the 19th century, aluminum was worth more than gold. Napoleon III even used aluminum cutlery for his most important guests, while the others had to settle for gold. Everything changed in 1886 when a discovery made aluminum accessible and affordable. 2 scientists working independently, the Frenchman Hall-Héroult and the American Charles Martin Hall, developed an electrochemical extraction process still used today. They discovered that by dissolving aluminum oxide in a salt called cryolite and applying electricity, the oxygen atoms separated, leaving metallic aluminum behind. This method made it possible to produce aluminum in bulk at a much lower cost, thus revolutionizing the industry. But where does aluminum come from? It lies just beneath our feet. It attracts miners because it is the most abundant metal in the Earth's crust, making up more than 8% of its composition. However, aluminum does not exist in its pure state in nature. Unlike gold and silver, it does not appear as nuggets or veins. It is found only in deposits of reddish bauxite. The richest deposits are located in Australia, Guinea, Brazil, and Jamaica. The Alcoa mine is located in the heart of the Australian mountains. These mountains are mainly composed of bauxite and form the largest mine of this, or in the world, with about 23 million tons extracted per year. However, most bauxite deposits cannot be exploited without first drilling through an underground rock barrier more than 5 meters deep. This requires explosives powerful enough to demolish a 10-story building. The rock is first drilled, then the explosive, made of ammonium nitrate combined with fuel, is inserted. Each month, they use between 700 and 900 tons of ammonium nitrate. Thousands of tons of ore containing aluminum oxide are blasted every day. Each explosion opens about 2 hectares of land and releases between 50,000 and 100,000 tons of ore. Each ton of ore may contain only a few kilograms of aluminum. A large quantity of bauxite must therefore be processed to produce a single ingot. To obtain 1 ton of aluminum, about 4 tons of bauxite are needed. Extraction requires billions of dollars of investment. Today, the price of aluminum is $2.65 per kilogram, and the mining industry invests in large-scale equipment. This excavator is the largest in the world, costing more than $20 million, making it one of the most expensive. Off-road trucks can transport up to 270 tons of bauxite, and the excavator loads 1 ton in just 3 moves. A truck arrives empty and leaves loaded in only 1 minute. The trucks then unload the ore at the processing plant. To extract aluminum from the ore, a refining process called the Bayer process is used. A conveyor belt deposits the ore into a giant rotating drum where enormous steel balls grind it into a fine powder. The bauxite powder is then mixed with a caustic fluid that separates the aluminum oxide from the rest, producing a concentrated aluminum oxide solution. And then comes the most surprising part. This solution dries and forms sandy crystals called alumina, the substance from which aluminum is made. The next step is to isolate the aluminum from the oxygen. To do this, the alumina is transported to an Alcoa production plant. A loaded ship leaves port every 3 days. The alumina it carries will be transformed by a smelter into 35,000 tons of pure aluminum. Every 3 days, a ship arrives with about 100,000 tons of alumina. Its contents are then completely sucked up by a massive industrial vacuum that extracts about 300 tons per hour, emptying the ship in about 5 hours. The material is then deposited onto conveyor belts and transported to the plant where the alumina is introduced into large electrolytic cells filled with molten cryolite. Cryolite lowers the melting point of alumina from 2050 degrees C to about 950 degrees Celsius. To obtain pure aluminum, it is necessary to separate the oxygen atoms that hold it tightly together. This process requires enormous amounts of electricity. That is why aluminum is called electricity in solid form. Electricity consumption represents about 1/3 of the cost of 1 kilogram of aluminum. The energy used by the plant to power the cells could supply 300,000 households. In total, more than 340 megawatts of electricity are consumed each year to produce aluminum. In the electrolytic cells, a low-voltage, high-intensity electric current is applied through carbon anodes and a cathode, thus triggering electrolysis. Electricity flows through copper rods connected to the cells. The aluminum oxide molecules they contain are composed of 2 aluminum atoms and 3 oxygen atoms. The electric current breaks these bonds, separating the atoms. The oxygen rises to the surface of the container and reacts with the carbon anodes to form carbon dioxide, while the denser aluminum sinks to the bottom. After electrolysis, the molten aluminum at about 950 degrees Celsius is separated from the cryolite by suction pumping. This process takes place in continuous cycles every 36 hours to extract the metal from the cells. Once extracted, the liquid aluminum is transferred into a transport crucible, a thermally insulated container designed to maintain the metal's temperature and prevent premature solidification. In the refining furnaces, the aluminum is reheated to remove the remaining impurities using processes such as filtration, which eliminate unwanted elements like hydrogen and oxides. The pure aluminum is then cast into molds to form ingots, then subjected to controlled cooling to ensure solidification without structural defects. Once ready, the ingots are sent to various industries where they become product for the automotive, aerospace, and construction sectors. But don't leave yet. What follows in this video is just as interesting and impressive. Don't forget to leave a like on this video and subscribe to the channel so you don't miss any of our upcoming videos.
There are moments when you walk on the warm sand and you can already smell in the air that salty scent that announces the ocean. You move forward slowly. The waves in the distance seem to call to you, and you already know that you will not be able to resist the urge to taste this mysterious water that stretches to the horizon. It looks so gentle from here, but we know that a simple touch on the tongue will reveal all its saline strength. We approach, we dip our hand into this moving expanse. We bring it to our mouth, and then it is an explosion of salt that immediately surprises our taste buds. This taste, so strong, is the very signature of the Atlantic Ocean, and yet it is not the only one to hold this secret. Seawater in its complexity contains on average 35 g of salt per liter. A simple piece of data, but one that hides fascinating nuances, because depending on the seas and oceans, this salinity varies, ranging from 35 g in the North Atlantic to 38 g in the Mediterranean, and much more in certain expanses such as the Dead Sea, which can reach up to 260 g of salt per liter, a true sea of crystal invisible to the naked eye. On the other hand, some waters, like those of the Baltic Sea, contain less than 10 g per liter, giving each sea a unique personality. This salt is mainly sodium chloride. A simple formula that nevertheless tells a whole chemical and geological story. A sodium ion, that is to say an atom of sodium that has lost an electron, joins with a chloride ion, an atom of chlorine that has gained an electron. Together, they form what we call table salt, the one we sprinkle delicately on golden fries, without thinking that it has traveled billions of years before arriving there. But in seawater, chloride and sodium do not hold hands. They move separately like two companions who only meet again when conditions allow. And it is when the water evaporates that these two elements finally come together, sharing that electron so sorely lacking in one and so abundant in the other, a gesture of chemical solidarity that is almost poetic. But this story does not end there, because the question we naturally ask ourselves is, where does all this salt come from? We must go back nearly 4 billion years, to a time when the Earth, still young and boiling, was nothing but a succession of active volcanoes spewing steam and gases into a still hostile atmosphere. Among these gases, sulfur and chlorine, which mixed with the newborn water, would dissolve into the first oceans, already giving a salty taste to those primitive waters. And if chloride brings the flavor, sodium makes our taste buds more sensitive to this perception, creating a unique sensation that we still know today. Sodium, like potassium, magnesium or calcium, is also found in the rocks that cover our planet. And since forever, rain through its runoff has torn these elements from the mountains and carried them to the oceans. A cycle that has never stopped. Rivers and streams all over the world pour more than 2 billion tons of minerals into the seas every year, perpetuating this invisible link between the Earth and the ocean. At this point in history, we must pause. Because if this scientific and natural adventure fascinates you, then you must subscribe and activate the bell. Because what you are discovering is only a tiny part of the wonders we will explore together, and you definitely don't want to miss what's next. But let's return to this intriguing question. Why does salinity remain stable? Why does the salinity of the ocean not continue to increase when its inputs are constant? It is because the environment also absorbs these elements, naturally balancing the system. Potassium, for example, is fixed in the clay present at the bottom of the oceans. Calcium is captured by marine organisms that build their shells, and sodium itself integrates into volcanic rocks. Thus, for millions of years, the level of salt in the oceans has remained remarkably stable. Yet despite this balance, it must be remembered that this water is undrinkable for humans. It is a question of osmosis and cellular balance. Our countless and fragile cells contain water and mineral salts. When we consume a very salty food, the salt disperses around our cells, creating a higher concentration outside than inside. To restore balance, the water contained in the cells migrates outward, seeking to dilute this excess salt. But this migration deprives our cells of hydration, leaving us even thirstier than before. That is why drinking seawater does not quench thirst but worsens dehydration. Thus, the ocean is a perfect kingdom for swimming, floating or letting yourself be carried by its waves, but certainly not for quenching your thirst. And perhaps that is the true beauty of this infinite expanse. It welcomes us for play, for contemplation, for adventure, but it keeps its salty treasure for itself. So the next time you set foot in the Atlantic, the Mediterranean or elsewhere, you will know that every drop that touches your skin carries a story billions of years old. And you may think, smiling, that this taste on your lips is not just a simple natural seasoning, but the trace of a journey that began long before your birth. For the ocean, in its infinite patience, is not content to be just a landscape. It is the liquid memory of our planet, and every wave that breaks is a page of this endless book. Welcome to the most delicious show on YouTube. Today, we are going to travel through the wonderful land of chocolate, the M&M's factory. We all love these little bites of happiness, but have you ever wondered how they are made? In this video, we will take you behind the scenes of the production, from start to finish. From the ingredients used to the ultramodern machines, you will discover what makes these coated chocolates so irresistible. So get ready to satisfy your sweet tooth and join us on this exciting journey through the world of M&Ms. M&Ms are every candy lover's dream, and their delicious taste comes from a carefully crafted combination of ingredients. First of all, M&Ms are made of specially formulated chocolate to achieve the perfect texture and flavor. It is composed of cocoa mass, cocoa butter, and milk powder, which give it a rich and creamy taste. Then there's sugar, lots of sugar. M&Ms are sweetened with a mix of crystal sugar and corn syrup. The corn syrup helps keep the candy soft, while the crystal sugar brings the sweetness we all love. M&Ms come in a rainbow of colors. From the classic red and green to more original shades like turquoise or purple. The food coloring is applied through a liquid coating that covers the chocolate center. Every ingredient is carefully selected, sourced, and tested to ensure impeccable quality. The cocoa comes from Ghana, Ivory Coast, and Indonesia, and the sugar is also checked to guarantee its purity. Flavor scientists are constantly creating new varieties to surprise the brand's fans. Every bite has to be as delicious as the last. M&Ms are produced in a large factory where every step is strictly controlled. The first step is molding the chocolate into small spheres. Then comes the coating with sugar, corn syrup, and sprayed colorings, polished in a rotating drum to give them their shine. After that, the M&Ms are sorted by color and sent to the packaging line. Automated machines and robots pack them into bags, boxes, or tubes of different sizes. A sensor machine sorts the candies by color. Another one, called the end rover, applies the coating and can process hundreds of thousands of M&Ms in just a few minutes. The entire production line is optimized to reduce waste and improve efficiency. Heat is recycled to dry the candies, and the packaging uses a minimum of material. Quality is an absolute priority. Every ingredient is tested to remove impurities and contaminants before being used. The chocolates undergo tests on their texture, taste, and appearance. One original test is the drop test, where candies are dropped from several meters to check the strength of their coating. They are also tested under different temperature and humidity conditions to guarantee freshness. M&M's also conducts regular audits of its suppliers and factories. After all these steps, the final product is an irresistible candy enjoyed all around the world. M&M's come in several varieties. Classic milk chocolate, dark chocolate, peanut, crispy, peanut butter, almond, and caramel. Each variety has its unique taste and texture. M&M's are available in many packaging formats, from small individual bags to large sharing packs. They have become a cultural icon, perfect for parties and events, loved by children and adults alike. And that's it, the behind-the-scenes tour of the M&M factory is over. We hope you enjoyed discovering the ingredients, the production process, the quality control, and the final product. And you, do you have a favorite variety or a memory linked to M&M's? Share it in the comments, and don't forget to click the like button and subscribe for more delicious content. Have you ever wondered why a modern technology is called Bluetooth? Admit it, it's a rather strange name. A wireless technology that connects your headphones, your speakers, your car, your keyboard, and even your fridge. Yet, it was given the name of a tooth, and blue on top of that. It sounds more like a pirate than an innovation. And yet, behind this slightly odd name lies a fascinating story that takes us back directly to the Viking era. So stay tuned, because by discovering this story, you'll realize that in your pocket you carry a heritage that's over 1,000 years old. Welcome to the channel that explains as simply as possible how the things around us work. Before Bluetooth, wireless communication was a real nightmare. In the 1990s, if you wanted your phone to talk to your computer or your mouse to work without a cable, it was almost impossible. Each company created its own short-range radio system, and nothing was compatible. As a result, if you bought a keyboard from one brand, it could refuse to work with your PC from another brand. Imagine a world where each company invented its own Wi-Fi. That's exactly what it looked like. So in the mid-90s, giants like Ericsson, Intel, Nokia, and IBM decided to join forces to create a common standard. A simple, low-energy system capable of easily connecting very different devices. This project eventually became Bluetooth, but there was still one huge problem. It needed a name. Finding a name sounds easy, but in reality, it's a real headache. It had to be short, easy to remember, and most importantly international. Not too technical, not too bland, and distinct enough to stand out in a world full of acronyms like USB, Wi-Fi, or GSM. For a while, the engineers only had a simple code name for the project, and that's when a surprising idea appeared: Bluetooth. At first, it was supposed to be temporary, almost a joke among them. But in the end, this original name stuck. And all of this thanks to a Danish king who lived over 1,000 years ago, back in the 10th century, Harald Bluetooth, the Viking king of Scandinavia. A king named Harald Gormson, better known by the nickname Harald Bluetooth. He ruled Denmark and part of Norway around the year 958. His great achievement was uniting the Danish tribes into one kingdom and spreading Christianity in the region. He was seen as a mediator capable of bringing rival clans together. But why call him Bluetooth? Historians don't all agree. The most widespread theory is that Harald had a dead tooth that appeared bluish-black, hence the nickname. Another theory mentions an old word that described people with a very dark complexion. Either way, the nickname stuck and survived for over a millennium. And the story doesn't end with the name. Look at the Bluetooth logo. It looks like a simple triangle stuck to a line, but in reality, it's a Viking symbol.
A Beintrun, a mix of two Nordic rune. One represents the tache for Harald, the other the B for Bluetooth.
So every time you see that little logo on your phone or your headset, you're actually looking at the initials of a Viking king written in an alphabet over 1,000 years old. The very first Bluetooth device came out in 1999. It was a hands-free kit for cell phones. At the time, it was almost science fiction. Talking on the phone without a cable seemed incredible. In the early 2000s, the technology appeared in phones, computers, and many accessories. Over time, it became so common that its name blended into the background. Today, no one wonders why their headphones are called Bluetooth. It's just become normal. But behind every connection lies the heritage of a Viking king. And today, Bluetooth is absolutely everywhere. Every year, billions of equipped devices are sold. Wireless headsets, controllers, smartwatches, medical equipment, embedded systems, modern appliances. The technology has advanced enormously since its beginnings. The first versions were slow and limited. With Bluetooth 5.0 and beyond, we now have faster speeds, lower power consumption, and the ability to connect multiple devices at a distance. Yet, despite all these evolutions, the name has never changed. No matter the progress, we still call it Bluetooth, an old Viking nickname that lives on in the digital age. So why does this story matter? Yes, it's a fun anecdote, but it's also proof that human history and modern technology often cross paths in unexpected places. Instead of a cold name like Short Range Radio Protocol 1.0, we got a name with character, a name that intrigues and sticks. It reminds us that even in high technology, creativity and storytelling play an essential role. So next time you connect your headphones or link your car speaker, think about this. You're using a technology that carries the name of a Viking king from more than 1,000 years ago. A king with a mysterious Bluetooth who united warring tribes, and whose initials are engraved in that little symbol on your screen and in the very connections in your pocket. Thanks for following this story about an everyday technology. Don't forget to like, subscribe, and stay with us for more hidden stories in the details of daily life.